This video is about free body diagrams. Question 1. What are the steps to drawing and labeling a free body diagram? So, step 1, circle the object. Step 2, label all of the external forces on the object with an arrow to show the direction and magnitude of each force. Step 3, draw a convenient x and y axis to minimize vector components. And step 4, for each object, apply Newton's second law of motion for each axis. So for this video, we're only going to go over steps 1 and 2. So this is an example, or these are two examples of free body diagrams, where you circle the object and you label the forces. So, question 2. Label the forces on the following diagrams. Part A. A block is at rest on a horizontal surface. So if a block is at rest on a horizontal surface, nothing is pushing or pulling it. So read this on the bottom. The total length of the vertical force pointing up must be equal to the total length of the vertical force pointing down. It's difficult to draw exact magnitudes, but you can see the force of normal is up, force of gravity is down. Force of normal points from the surface of the object, force of gravity points from the center of the object. Part B. A man is pushing a block to the left with the horizontal force on a rough horizontal surface. The block does not move. So the block doesn't move. So sigma F equals ma. The total forces on the object equals the mass times the acceleration of the object. So if the object has no acceleration, because it's not moving, if ma is 0 on the right side, then sigma F is 0 on the left side. So force of push in magnitude should be equal to force of friction in magnitude, because the object doesn't move, the acceleration is 0. Sigma F equals ma. Force normal up equals force gravity down, because the object doesn't move up or down. So read what's written here. The total length of the vertical force pointing up must be equal to the total length of the vertical force pointing down. And the total length of the horizontal force pointing to the right must be equal to the total length of the horizontal force pointing to the left. Acceleration is 0, so sigma F is 0. Remember, we're always referring to sigma F equals ma. Part C. An object is being pushed to the left on a wall. So force of normal is always 90 degrees from the surface. The force of push is from the contact. Force of friction is from the surface, and the force of gravity is from the middle. So the total length of the vertical force pointing up is equal to the total length of the vertical force pointing down. And the total length of the horizontal force pointing to the right is equal to the total length of the horizontal force pointing to the left. Because remember, sigma F equals ma, the object isn't moving, acceleration is 0. Part D, a man is pushing a block on a slope which is 20 degrees from the horizontal on a rough horizontal surface. The block does not move. So, on the left side, the man is pushing the block downwards. The push is parallel to the slope. Remember, the block doesn't move. So the total length of the vertical forces should be the same as the total length of the total length of the vertical forces pointing up must be equal to the total length of the vertical forces pointing down. And the total length of the vertical forces pointing to the right must be equal to the total length of the vertical forces pointing to the left. It's difficult to draw these vectors with a perfect magnitude. The question on the right side, the man is pushing the block upwards. The push is parallel to the slope. So once again, the block doesn't move. So The total length of the vertical force pointing up must be equal in length to the total length of the vertical forces pointing down. And the total length of the horizontal forces to the right must be equal to length to the horizontal forces in total to the left. Because remember, sigma f equals ma. If the right side a is 0, then the left side sigma f is 0. Question 6. A dead fish is floating on top of the plastic radioactive ocean water. So it's just floating. It's not moving up or down, left or right. So the total length of the vertical force pointing up must be equal to the total length of the vertical force pointing down. Buoyant force pointing up equals buoyant force pointing down. Sorry, buoyant force pointing up equals force of gravity pointing down. Part F. A block is at rest and is hanging from the ceiling by one massless string. So force of tension up equals force of gravity down. So those lengths should be the same. Once again, sigma f equals ma. If the object isn't moving, a is 0, so sigma f is 0. Question 8. A block is at rest and is hanging from the ceiling by two massless strings. So we got two forces of tension. We got one force of gravity. Remember, force of tension is from the string. Force of gravity is from the middle. So the total length of the vertical forces pointing up must be equal to the total length of the vertical force pointing down. And the total length of the horizontal force pointing to the right must be equal to the total length of the horizontal force pointing to the left. Part H. A block is tied to a massless string and is raised up at an angle theta from the vertical. So look at the problem on the left side. The block is released from rest. So the magnitude of force gravity should be greater than the magnitude of force tension because it's going to be moving down. The problem in the middle, the block is now at the bottom of its motion. The magnitude of force tension up should be greater than the magnitude of force gravity down, because the block is going to go up 1 moment later. Now look at the problem on the right. The block is now at the top of its motion. Once again, the force of gravity down should be greater in magnitude than the force of tension. So once again, these are not always drawn to scale because they're quite difficult to draw to scale. Part I. A car is moving in a straight line to the right with a constant speed. Look at the problem on the left, on a smooth horizontal surface. So the total length of the vertical force up is equal to the total length of the vertical force down. And the total length of the horizontal force to the right must be equal to the total length of the horizontal force to the left. But in fact, it's on a smooth surface, so there's no friction. So there is no force to the right or the left. Now look at the problem on the right. The car is moving in a straight line to the right with a constant speed on a rough horizontal surface. So force of push is equal to force of friction. Force of push to the right is equal to force of friction to the left. And force normal up equals force gravity down. You see force normal points from the surface, force gravity points from the center, force push points from the contact, force of friction points from the surface. Part J. A car is moving in a straight line to the right on a rough horizontal surface. Rough means there is surface friction. If the car is slowing down, that means force of friction is to the left. If the car is speeding up, that means there's a driving force or a force of push to the right and force of friction to the left. And you could see the force of push or the driving force is greater in length than the force of friction to the left. Part K. A man pulls a massless string which is attached to a block with a constant speed. at an angle theta above the horizontal on a rough surface. Label the forces on the block, not the man. So, we got force of pull, force of normal, force of gravity, force of friction. You notice force of normal is really short in length. The magnitude of force normal is really small. That's because the total length of the vertical forces pointing up must be equal to the total length of the vertical forces pointing down. So what forces point up? We got force pull and force normal. So force of pull vertical plus force normal vertical should equal force gravity down. And it says that the block is moving with a constant speed. So sigma F equals ma. So force pull to the right should equal force friction to the left. Part L. A ball is thrown vertically up and is moving upwards. If there's no force of air friction, there's only force of gravity as it moves upward. If there is force of air friction, force of friction and force of gravity both point down, because force of friction here is opposite the direction of motion. Part M. A ball is thrown vertically up and is at its maximum height. At its maximum height, velocity is 0. So it doesn't matter if there's air friction or no air friction, we only have force of gravity. Because air friction depends on velocity. If velocity increases, then air friction increases. There's no velocity, so there's no air friction. Part N. A ball is dropped from rest from the top of a very tall building. There is no force of air friction. Draw a free body diagram of the ball the moment the ball is dropped, when the ball is halfway down, and just before the ball strikes the ground. So the force of gravity only points down, and they should be all equal in length. Okay. Because force of gravity is equal to mg. So if all three images have the same mass ball, g is 9.81 down, the length should be the same of all three of them. Part O. A ball is thrown downwards from the top of a tall building. Draw a free body diagram of the ball the moment after the ball is thrown in. There is no air friction, and there is a force of air friction. So remember, look at the image on the right. When we threw the ball upwards, and the ball goes up, force of friction is down. Now that the ball is going down, force of friction is up, because air friction is opposite that of the motion of the ball. Part P. A ball is released from rest from the top of a very tall building. There is air friction. Draw a free body diagram of the ball a few seconds before the ball reaches its terminal velocity. You could see force of gravity in magnitude is greater than force of friction in magnitude. The exact moment the ball reaches its terminal velocity. Terminal velocity is when sigma f equals ma, sigma f is 0, a is 0, v is constant. So if v is 0, if a is 0 and v is constant, then the magnitude of force gravity down has to equal the magnitude of force friction up. And a few seconds after the ball reaches its terminal velocity, the second image and the third image should be exactly the same, where the magnitude of force gravity down equals the magnitude of force friction up. So you could pause the video and read this. Part Q. A ball is thrown at an angle theta equals 45 degrees north of east from a horizontal surface. Draw a free body diagram of the ball the moment the ball is thrown when there is no air friction. If there's no air friction, there's no force of friction. So that's the image on the left. If there is air friction, we're going to have force of friction, because as velocity increases, air friction increases. And it's opposite that to the direction of motion. Part R, a ball is thrown at an angle 45 degrees north of east from a horizontal surface. The ball is at its maximum vertical height. So on the left, there is no air friction. So we only have the force of gravity. On the right side, there is a force of air friction. So we do have a force of friction opposing the motion. Part S, a block is being pulled vertically upwards by a massless string pulley. The speed of the block is constant, so force of tension equals force of gravity to the image on the left. Look at the image in the middle. The block is accelerating. So the force of tension up should be longer than force of gravity down. And finally, the block is slowing down, but it's still being moved upwards. So the force of gravity should be longer than force of tension. Part T, a block is at rest on an incline. There is surface friction, so it's not moving. So remember, force normal is 90 degrees to the surface. And if the block is at rest, that means force of friction should point to the left. So the total forces to the left must be equal to the total forces to the right. And the length of the total forces up must be equal to the length of the total forces down. Part U, a block moves down an incline. There is surface friction. So it's moving down an incline. If the speed of the block is constant, the total length of the forces to the left must equal the total length of the forces to the right. Now, on the right side, it says a block accelerates. So the length of the total forces to the right, this is a mistake. It should say down. Must be longer than the length of the total forces up. Because you could see the block is accelerating downwards. So this should say down. Part V, a block is pushed up an incline. There is surface friction. The block slows down. That means this force, a block is pushed up an incline. There is surface friction. So for this first image on the left, force of friction should be longer than force of push. Second part, the speed of the block is constant. So force of push should equal force of push to the left, should equal normal force and force of friction to the right. Finally, the block speeds up, it accelerates. So the force of push to the left should be greater than force of normal to the right and force of friction to the right. Part W, two blocks are attached to each other by a common string. There is a surface friction. So circle the objects because we have two objects. And you could see with this image on the left, the object on the incline, we have normal force, force of gravity, force of tension, force of friction. The block hanging is only force of tension, force of gravity. And this image on the right, both objects have a tension force and a gravitational force. Part X, a mass lying on a horizontal surface is attached to a spring and is stretched from its equilibrium position. It is then released. So at the equilibrium position, x equals 0, the object will not move left or right. Once you stretch it to x equal plus a, and you release it, this mass on a spring will accelerate to the left. That's why force of spring is longer than force of friction. And force normal in length should be equal to force of gravity in length.